All right, it's time. So, any questions from the homework? Nick?
Can
Oh,
you go over 4.3, number 17, please?
oh, for this one, I have to go over. Let's see. Oh, I think you only have question with the first one. Then it's easier. You were asking how to do. How to approximate. This value here. Okay, so clearly we need to use the linear approximation. So when you have linear approximation, you basically write this down. Because it's approximation, it's roughly f negative 5 prime. Okay, so we're trying to see what happens to 4.97 by what happens at 5. Once you have that, you can go to the graph and observe this one equals 4. Once you have these two information, now the bottom actually, you know, it's going to be so the whole thing. So I think the only thing you're missing is the derivative, but you have to get it from the graph.
Okay, thank you.
Okay, I saw Julia. Do you still have a question?
Oh, that was the one I had a question about.
Okay. Anton?
Yeah, so I kind of had a question about typing things into WebWork.
Right.
I was kind of having a problem with just for ones that I had multiple increasing or decreasing, I would get everything else right except for that one, and it would say like cannot convert a list of intervals to an interval.
So use a union.
Okay, I just put a
Capital
U
U.
in between.
Capital U, yeah.
A capital U. Okay, great. Thank you.
Nathan?
4.4, number 13.
Okay. This is L'Hopital's rule, so you can plug in everything you find. This is infinity minus infinity, so it's impossible to do it directly. Therefore, we use the property of Ln. Sounds good? Okay. Now, what's the derivative? What's the limit of the inside? Well, it's going to be, hold on, what did I do? Okay, yeah. This one is going to be 0 over 0 if you plug in x equal to 1. Therefore, I can apply L'Hopital's rule to this. due to the L'Hopital's rule. And because I have 0 over 0 case. Now, once you switch that, can you plug in 1 now? 2/3. Then the whole thing is ln 2/3. Okay, so your job is try to create a 0 over 0. Once you have that, period. Okay. Yeah, the first time I saw things like this, I was pretty surprised. Like the answer is going to be ln 2/3. I was thinking like this is ridiculous. X to the 6, X to the 9. I either got 0 or infinity, but somehow they got something like this. Okay. Other questions? All right. If no question, we move to section 4.5, curve sketching. Summary of okay. Basically, what we do is we just add what we did for 4.3, where we know f prime x. We can find increasing, decreasing. Therefore, local max, local min. We also did second derivative. We can tell concave up, concave down. We can tell inflection points. That's what we did in 4.3. Now for 4.5, they just want to actually take the whole package to add in everything we know before, including domain, vertical asymptote, horizontal asymptote, XY intercepts. Okay. And finally, symmetry, which means odd or even function. Okay. So this is almost like a review session. Nothing is new, but just to put everything you know together. This is the new thing we learned. This will be everything we learned from before. Okay. What we will do for this section is I will go over one example. We can go over it all together. Then we will move on. In the exam, you will have exactly one problem, which is very similar to the one we are going to go over. And you do not need to memorize this list. I will ask explicitly what I'm looking for. Okay, so you don't have to remember there are 6 items. I will ask for what's the XY intercept, what's the horizontal asymptote, and so on. Okay, so all you need is try to know that what each one means. Okay, with that in mind, let's try the example. It's complicated, so I did the computation for you. We already know f prime x. And f prime prime x. We already know these two facts. Okay. So now can you go ahead and sketch the graph to reflect what we just wrote down from number 1 to number 6. Find the vertical asymptote, if any, horizontal asymptote, if any, XY intercept, if any. If there's any symmetry, try to identify it. Okay, and of course, with everything we learned from concave up and down, increasing and decreasing. Okay. Go ahead, try yourself. And if you get stuck, feel free to ask a question at any time. All right. Try to check your work with mine. See if there's any questions. Nathan?
On the exam, are we gonna have to show like how we found x-intercept and y-intercept and horizontal and vertical asymptote? Or we
Technically,
just,
no.
like, write it?
Like, they're pretty easy. Unless you have something really, really complicated. Like, okay, if you have something like this. And somehow just tell me, okay, x equal to 2. Well, that's less trustworthy. You probably want to show the work. Otherwise, I mean, we're doing things remotely. Maybe you just type in Wolfram and they give you the answer. Right? So anything like that, you probably want to show a little bit of work. But for things like this, it's basically, it's either this is 0 or this is 0. 0 and 6 will be straightforward. So yeah. Don't write anything that you, I would say don't write anything that you feel like it's sketchy. Right? So yeah. All right. If no question regarding this, now let's take the information and try to draw it. Okay. It should be interesting. Number one, you have two intercept, 0, 0, 6, 0. And same thing with the y-intercept. Second, you want decreasing, increasing, decreasing, decreasing. So that's roughly it. Okay. After that, you want to use the second derivative to solve it. So what you have is concave down. It looks weird, but you probably have to do this. Well, that's the best you can. Concave down from 0 to 6. Make sure you still have the asymptote, the maximum here. So finally, concave up. For decreasing, you don't have a choice. It has to be this. Does everything make sense? How to draw this? Looks weird, right? We haven't seen any graph like this before. Particularly the things weird are here. Like according to what I just draw here, you have a sharp turn. But then if you go back and think about it, how did you get 4, 0, and 6? Well, for 4, you got it from here. That's where your derivative equal to 0, where everything is smooth and it's just horizontal. Makes sense. For the rest too, how did you find them? You find it from here and here. That means that's where your derivative does not exist. Well, technically what I draw here, the derivative does not exist due to the sharp corner. And here, the derivative does not exist because the whole thing is vertical. So at first, this looks weird. Second thought, it makes sense. Okay. Any question regarding this? If no, we will just check it with Desmos, see how much we can actually match what Desmos does. We have, hold on, let me share the screen. Dun, dun, dun. We have y equals 4x to the e 2/3 times 6 minus x 1/3. This will be what Desmos tell us. Okay. Decreasing before, increasing after, decreasing, decreasing after, concave down, concave up. We got inflection point here. We got the local minimum here, local maximum here. So everything just matches what we have. Plus, this whole thing here is sharp corner, but with some additional analysis, we find it's pretty reasonable to have something like that. So I would say we did a decent job of doing the graph. Not perfect, but all the important information are there. All right. Does everything make sense for this particular example? We can do more in class, but I would just say, like, yeah, go ahead and try to do everything by yourself for the web work. Bring them to class if necessary. In the exam, you would definitely have something very similar to this. A thing which I just give you something like that. If it's complicated, I will calculate the first and second derivative for you, and then ask, can you collect the information I want, like intercepts, increasing, decreasing, local max min, concave up and down, things like that. Finally, draw it. The expectation is you can finish a problem like this within 10 minutes. If you feel like with all the work we just have done, you can finish the whole thing in 10 minutes, you will be all set. Okay? If it's longer than that, practice more. All right. Now we move to optimization. A very, very important section. Remember, the whole point of doing maximum and minimum is trying to say, hey, where can I maximize my profit? Where can I have the minimum of my cost? How do I buy stocks? How do I open a company? Things like that, right? Finally, we're going to touch that. And of course, we're going to have a baby version. Later, if we have time and you guys are interested, I can give you some real life applications, which is real scale. But for now, let's just look at the easy ones. A farmer has 800 feet fence to fence off a rectangular field. How to arrange the dimension? To cover the biggest area. This will be a typical optimization problem due to this word biggest. That means you have a freedom to choose that dimension. Some of them give you a small area, some of them give you a bigger area, and there will be one best configuration which give you the best area, in this case, biggest. Sounds good? Let's take a look. What do you mean by that? That means your area is determined by your dimension. Okay, you have 800 fence. You can do something with a rectangle, which is a square. If you do dimension like that, your area is going to be 40,000. If you do arrangement like that, for rectangle, you're going to have 30,000. Okay. And if you want to try something interesting, you can do 1 feet here, 1 feet here, 399 here, 399 here. That's 800 fence. And congratulations, you have 399 square footage, which is a disaster. Okay, you wasted all the material almost. Can you see that for different arrangement, you have different area? Then clearly, for some kind of arrangement, you have the biggest area. So far, the biggest one is here. Okay, but maybe there is another dimension which is even bigger. Okay, from here, now we are going to solve this problem. You are trying to find the biggest area, which depends on the dimension. So what we would do is we would try to write area as a function of your dimension. When your dimension change, your area change. Still okay? After that, to find the biggest area, we just need to find the absolute maximum of f, I would say x. How do you do that? Ending points, critical points, compare all of them, find the biggest. We have a standard way of doing that. So the harder part is try to do this. Of course, for this case, it's easy. Let's see how we do it. You're talking about the dimension of a rectangle. So basically, it's just the width and the length. We don't know what they are. But once you know, the area is nothing but x times y. Of course, you can't do it. You have two variables. But then you realize x and y has a relationship. Because you have a total of 800 fence, this gives you therefore, your job is try to take a different value of x in order to maximize this function, 400x minus x squared. Sounds good? Once you set up the function, how to find the absolute maximum piece of cake. Number one, you need an interval. Close the interval. How small can your x be? 0. How big can your x be? 400. Because I have 800 fence and I have 2x there. Okay. Maximum, well, ending points, and I need a critical point. Will this one ever be does not exist? No. Will this one be 0 ever? Yes. So we have 3 points. Which one is the biggest? Which one is the smallest? This will be the maximum area corresponding to x equal to 100, 200. Then the square one happened to be the biggest. Answer. The biggest area is 40,000 square foot when the area, let's say when the dimension is 200 by 200. the real work start from here. All right. Is everything clear? This is an easy example, of course. In general, the thing can get complicated, but the framework is straightforward. You want to maximize or minimize something, write that thing as a function. Okay, then the job reduced to find the absolute maximum or minimum of the function. How do you do that? 3 steps. Number 1, give it an interval, close the interval. Number 2, find absolute max and min. Number 3, compare them. Okay. Any questions so far? Let's try one more. A little bit harder. Okay, this time we have a cardboard. Okay. Now what we want to do is we want to cut out the same small square at the 4 corner. Okay, we cut them. Once we cut them, we fold the cardboard to make a cubic. Box with open top. Sounds good? Now question, how big is the small square we should cut in order to maximize the volume of the box? Okay, this is amazing. With the same material, basically, you start with the same material, you can make something really, really nice. You can make something really, really stupid. Okay, so basically, they're just trying to say, if you're smart enough, using the same material, you can make some bigger container. That is the dream case. Sounds good? What's your choice? Well, you can cut really small. I make a very, very thin box. I don't know how to draw it even. What's the good news? The good news is the area is going to be super big, the base area. The bad news is the height is really shallow. Okay, probably not ideal. What are your other choice? Well, you could cut it to be super big. If you still want to call it a box, be my guest. Now this one is super tall. The problem is the base area is super small. So you don't have a box, basically you have a stick. Sounds good? Can you see that the best way should be something, somehow you need to balance the height and balance the area at the same time in order to have the best volume? That's what we're looking for. All right. With that in mind, let's try to set up. You want some variable to reflect the dimensions. I would just personally take this to be x for the small square. Okay. Now what you need to do is just write your volume as a function of your x, and then find absolute minimum and maximum for which x. How do you do it? Well, the volume is going to be base times height because it's rectangular. Okay, remember this is 15, this is 10. Okay. What's the height? The height is just x. Can you see that? When you fold everything, this is your height. What's your base area? Your base area is going to be this once you fold it. Okay, that's going to be a rectangle, which equals the width times the length, which equals 15 minus 2x for the width, 10 minus 2x for the length, and x for the height. Is everything still okay here? All right, that's it. That's the function we're looking for. Now, please go ahead and try to find the absolute maximum. Okay, I'll give you a hint. Before you do anything, how big can your x be? Well, it can be 0, but no negative. What's the biggest value of x that is possible? What's the biggest? Half the size, right? Half of the shorter size. So the biggest you can do is 5. You cannot go beyond that because then you're basically at the middle point. All right, go ahead. Try to find the max. All right. Somehow I got the wrong number. So to start with, therefore I got a hard number. There's no better way but to use a quadratic formula to find what they are. You have two solutions and then you find, okay, one of the solution is definitely bigger than 5. So we don't consider it. We take this one. We try to calculate all the numbers to compare. We find this one is really harder to compare. So instead, what we can do is we can actually try to do the graph of this and find, well, on 0 to 5, the whole thing's like this. Therefore, this is going to be a maximum because that's an easier way than comparing for this case. Sounds good? Finally, we say this is the max on this interval. And we just answer the question backwards. All right. That's it. That's everything I need to go over in class about optimization. Tomorrow, we will do a similar worksheet as the related rates, which is on Canvas. It's about optimization. We have 4 problems, so you can do it in class. On Friday, I will answer any questions you have from that worksheet. Okay, so take this opportunity, practice by yourself, and let's do some harder problems together. That's all for today.